Yes. Coming to you live from Jacksonville, listening to the Motels. Only the Lonely classic. Come on, someone show up face to face. I feel like teaching a bunch of blank screens. Is there anybody there? Are you all in your beds? You're in your beds, aren't you?
I'd turn on my camera, but I'm all sick and gross and stuff.
Thomas is like, yeah, I'm in bed. Why do you think I'm on video off?
There's a lot of things you should see in this world, but my face isn't one of them.
Oh man.
Correct. I'm feeling good today. Got a fresh haircut. I've got my kayak necklace on. Whoa, life is good.
Looking fly.
I can fly. Motels are on. They came to Brit a couple years ago, and I listened to them live. Of course, the Motels are my ear. Old people tunes. Nice. Let's see. What shall we talk about? Seems like we gotta share a screen to start with. So let's do that. You don't always know what to do in the big picture, but you can at least do the next thing. Maybe for some of you, that will be the most important thing you learn today. Nice. Oh man, this is fun stuff. Let's see. So just for the fun of it, because it turned out to be quite a bit more complicated than I had anticipated, and I was actually surprised to realize I've never even looked into this. But I mentioned yesterday that the infinite series 1 over x squared, in other words, 1 over 1 plus 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25, it actually adds up to pi squared over 6. And I sent you an email yesterday with a link to a rather brilliant explanation. It's like from 1 blue, 3 brown, or I forgot the name of the website, but it's remarkably complex as to how that worked out. And I did happen to catch in the introduction to that was a problem that was proposed. I forgot what year. But that's one of the things that made, now all of a sudden I forgot his name. Oh my gosh, that's, shoot, whatever famous mathematician.
Was it Euler?
Euler, thank you, it was Euler. Wow, you even pronounced it right. Euler, Euler, not Euler. I guess he doesn't care, he's dead now, but probably one of the most prolific, certainly one of the most prolific, if not the most prolific mathematician ever. And it said in that video that this problem was actually what, I don't know, propelled him to fame mathematically, was he actually figured the dumb thing out, and given the complexity of the explanation. But anyway, the video, I say, it was kind of cool because this guy did a good job of trying to figure out how in the world did pi get in there, and he was talking, pi relates to circles, and the guy is brilliant. Anyway, you might find that interesting. It was only about 19 minutes long or something, but it probably left you with more questions than answers in terms of it being complex. I hadn't seen it before. But anyway, let's start off with something kind of cool here, in the sense that, along those lines, in the sense that it is a tremendous disappointment at how difficult it is to even figure these things out. In other words, let's say 10.4 continued. So we said yesterday, based on the p-test, I wonder what the history is on that. Why would it be p? I don't know. That if we took 1 over x to any power more than 1, well, let's raise it to something kind of nice, like 1.5. So since P, the exponent there, is more than 1, we said yesterday, bam, that's going to converge. And we'll discuss that a little bit more today too. Well, as long as X, and again, we typically don't use X for the letter just because X is usually a variable, meaning it permanently varies. And in other words, X stands for, well, everything, every number possible. And so we always kind of use some other letter for this. So if I start out at n equals, notice I can't start at n equals 0, right? Why not? Because then I'd have 1 over 0. So it kind of explodes there. And if you graph it, it's sort of infinitely tall. So, these will typically start at 1 or, some other number. So we can say based on the P test, this definitely is going to converge. But as I've been hinting at, that's not very satisfying in the sense that, great, it converges. The real question here in my mind is then, fine, to what? I want to know what this converges to. So Euler figured out pi squared over 6, if that p value was 2, it actually, came up with a perfect answer. And of course, thanks to, even patience, but certainly your graphing calculator or Excel, we could actually get an approximation of this. And as long as we're patient, it can be really accurate. But one of the things this chapter addresses that I think is really cool is the concept of error. And so, let's just bust a few of these out. If I type, boy, that feels like a waste of time. Let's just do it. 1 divided by 1 plus 1 divided by 2 raised to the 1.5 power plus 1 divided by 3 raised to the 1.5 power. I'm going to do 4 of them, plus 1 divided by 4 raised to the 1.5 power. So I just figured out S of, what do I call that? S of 4, because I just added the first 4 terms together. And I got approximately, because I'm even going to round off what my calculator says, I got approximately 1.671. And the next number happens to be 0, so that's a pretty decent round. Double checking that I actually typed what I thought I did. I got that, and so that's really cool. And so the question is, is that pretty close? Could we just quit right there? I want some of you to talk about think about this out loud with me, meaning you might not be right. Conjecture, guess, reason, just speak up. What's your thoughts on the accuracy of that? How do you address how accurate that answer is?
I think with some of them that would be accurate, but for a lot of them, you're gonna have to go out to probably at least 90 for things you'd see normally.
That's right. So some of them that would be pretty accurate. Other ones it may not. How do you tell, or why? How would we know if this was a reasonably accurate answer?
So is this assuming if we have the actual value that we can compare it to?
No, that's the problem. See, we don't have the right answer to this question. In a sense, it could be the case, and I actually don't know, that nobody knows. Nobody knows what this one's equal to. And so that's kind of fun. And by the way, if somebody does know the answer to that one, it would sort of stand to reason that they probably don't know the answer to this one, right? Probably nobody's ever asked that question before. Mm-hmm. Or perhaps some math nerd figured out a pattern, like a formula that works for all P. Who knows? That's what mathematicians do, right? But it's very possible that nobody knows the answer to this question. And as I said, that's the disappointing truth of these things. There's a ton of them that nobody knows the answer to. And that could be because it's impossible to get the answer, or it could just be, no one's figured it out yet. So in this particular case, is there any way to kind of have any idea how accurate this answer is, given that we don't have any other access to the perfect answer?
Well, we could compare then each number, to the previous number, and then see how close that is. And if it's in a certain range of accuracy that we want, we can leave it there to 5% or 1% or something. I don't know.
That's right. Comparing. In other words, if I went to S5, which I will do now, if I added the fifth term to this, it doesn't look like a 5. Plus 1 divided by 5 raised to the 1.5. I got 1.760. Doesn't that tell you something about accuracy? Like notice it grew by like roughly 0.1. Or the other thing I could do is figure out what is the actual number A4. Again, are you speaking the language here? S means you've added all of them up prior to that. So S4 means S1 plus S2 plus S3 plus S4. Or I should say, I'm sorry, I said that wrong. A1 plus A2 plus A3 plus A4. Well, if I actually figure out what A4 is, it's 0.125. And notice that's not very close to 0. So that would indicate kind of Raymond's point that, this one's going to take a lot more terms if you want a really decent answer. But also keep in mind, it depends what your purpose is, right? If you're ordering if you're using this to order fertilizer for your front yard, like, oh, I'm within 0.1, close enough, I'm good. And again, true mathematicians would never be satisfied until they can write an equal sign. Approximately equals never good enough. And so you actually can say something about error just based on, well, the fourth number is 0.125. That's not very close to 0. So this answer is not that good yet. So, but wouldn't it be interesting to be able to kind of like I'd like SN. I'd like to know what value for N so that it's say accurate to 2 decimal places. I mean, wouldn't that be kind of cool if you're saying, okay, fine, we have to give up and punt and we can't actually know the right answer. But I'd be happy if I was accurate to 2 decimal places. And so, how many terms do I need to add up? Wouldn't that be kind of cool? So, I mean, you could still do it manually, but it'd be nice to know when to quit, right? In other words, it's still going to keep on going out there and become accurate to the 6th and 9th and 20th decimal place and so forth. But it'd be nice to know, could I stop? And it turns out there's an answer to that question. It's rather beautiful and rather simple. And I'd like to show you how that works. If you did dive into the 10.4 assignment yesterday, you might have came to a stop, realizing the first questions were actually asking about this, and you went, I don't know what to do. So let me show you something cool. As if I had any other options. Everything I'm showing you is cool. Take a look at this. This is actually a page out of your book. This is page 678, if I remember right. And this illustrates a formula that I'm going to show you. And all I want to do is give you just sort of a quick conceptual understanding of this. But take a look at this right here. Let's see, let's look at this one down here. So for us, we started with, n was 1, and then n was 2, and then n was 3. And so when we started at n is 1, of course, you add 1 to that, and then you add 1 to that. And so, this is all of our numbers. And so isn't this what we're doing? We're plugging in a value for n, and we're getting kind of a certain answer out. We're getting kind of that area. And then we plug another value in for 2. And notice this would be considered a right-hand Riemann sum in a sense. And then we get another value and so forth, and we just keep adding those up. Well, do you notice that curve that's created there, does it make sense that the area of the rectangles will be less than the integral? In other words, it's underneath there, and so there's some wasted space, and so the area of the integral will be bigger. Your book is calling this Rn, as you can see up here. That area of the first n rectangles, like we just did S5 or S4, and so that was an area of 5 rectangles added together. Well, does it make sense based on this picture that that's going to be less than the integral of the function itself, whatever the function is? And for us a second ago, that function was 1 over x to the 1.5. Notice it has to be an x now, not an n, because now we're letting x be everywhere, not just individual numbers like 1, 2, 3, 4, 5. We're letting x be 1 and 1.1 and 1.8 and so forth, every single number possible. Well, the rectangles are underneath that. So certainly our estimate will be less than whatever that answer is. Isn't that kind of cool? Does that make sense? Well, cool. Like, in a sense, that's what we need to know. So let's go play with that just for this problem. This is one of the formulas that I want you to have down. The error feels like we need to change colors. Seems like it should be red. The error, which we're calling Rn, will be certainly less than, because it's underneath the integral from infinity to n, whatever function you're working with. And that function would be kind of our A of n formula. Certainly going to be less than that. Okay. All right. So what is our error for S of 5? So example, what's our error for our S5 that we just did a minute ago? We got 1.76. Great. But we're just wondering, how much that's off. Okay, well, according to this, we have to take the integral from infinity to n, I guess that's infinity to 5, right? Of 1 over x to the, let's see, I think I'll write it as 3/2 instead of 1.5 this time. Let me write one other thing here too, just to kind of help you visualize this before I kind of launch into that. If you take the actual sum in other words, from yesterday, that would be for 1 over x squared, that would be the actual answer, which we happen to know, pi squared over 6. And you subtract from that your estimate, because n is not infinity. Does that make sense? N is 5 or 6 or something like that. Does it make sense your sum will be larger than that? Because if you stop, then your answer is too small, right? Every time you stop, your answer is too small. You quit too soon. There's more. That collectively is what we're calling our error. I just want to make sure you kind of have the feel of what this is.
Doug, for this one, if we stop, aren't we slightly too big?
Not if we work on the left-hand side. I mean, it does, and this is why that language of, does it approach it from the top or does it approach it from the bottom? That is a significant question. And if we have negative numbers, then it's working its way down. And so that is worth considering, Connor. That's exactly right. But in our case, the answer to that is no, because our graph looks like, well, it looks just like that graph that I showed you a second ago that came out of the book. In other words, it's a decreasing graph. So it's positive and it's decreasing. So I can actually find the answer to this. Does it make sense to you that this would be kind of like the error? Because isn't that the part that we left off? Since we went from 5 to infinity, isn't it the part we left off? So for S of 5, we said, let's put in 1, 2, 3, 4, 5, and let's get an answer. And then if we go from there on, isn't that what we left off, if you will?
But couldn't we just go from 1 to infinity and then get our actual answer? Or would that not work out?
No, because in that graph, if we go from 1 to infinity, then we're going to be getting all of this air up here in these little spaces. And so, our problems are Riemann sums, because we're saying our values are 1, 2, 3, 4, 5, 6. We're not making our rectangles infinitely small. Our rectangles are 1 wide. Our change of x is 1. So there's air up there. So we're only getting an estimate from this.
So that's what confuses me. Because in this figure it shows that the error is the area, like those little triangles above the rectangles. How then is the integral from 5 onwards equal to that set of area?
It's not that area. It's actually this area out here. That's why if we say, what's the value, what's the error at 5? Well, then if we go from infinity to 5, from infinity to 5 is giving this area over here. Does that make sense?
Okay, so the figure is just trying to show you that Rn is always less than the integral.
That's correct.
Okay.
So yeah, I think some of the stuff I said in the beginning maybe made that a little bit confusing. So the focus of this graph is more the fact that we're figuring out that area that's left out on the top of that, out on the far right end of it. And yes, it's less. In other words, the error, it doesn't say the error is equal to that. Does that make sense? Why doesn't it say the error is equal? Well, that's because of all of these. If we knew the exact error, does it make sense we could just add it on to the answer and say, now we got it perfect? So the error is missing all of these. That's kind of the problem. So we can only say the error is less than that. So that symbol is pretty important. Okay. Okay, well, we can actually take that integral since that's really x raised to the -3/2. And if we add 1 to that, it becomes x to the -1/2. And then we have to divide by that answer. I'll be correct and show that I have taken the integral, but I don't really want to plug these numbers yet because I'm confused by this. Dividing by -1/2 is like multiplying by -2, and x to the -1/2 would move to the bottom as x to the +1/2. That's a nicer way to write it. Do you agree with that? Algebraically, so that I can go plug in infinity and in 5. And as I said yesterday, we're just going to be lazy about this. What happens to this expression when you put large numbers in there? Not so much plug infinity in, as I said, but put large numbers in there.
It gets smaller.
Exactly. So again, mathematicians would cringe at this, but if I put this in, and again, that honestly, that's one of the things that annoys me about mathematicians. All this rewriting limit and so forth. Like, you can understand the idea without confusing people with the concept. It just means large number. This just means big number. It doesn't mean I'm putting infinity in. Infinity is not a number, just big number. Well, yeah, exactly. That's on its way to infinity as well. Now, again, the square root hampers it because, what used to be 100 is now reduced to 10, but it's still on its way to infinity. And then 2 over infinity is on its way to 0. And then when I put 5 in, I get this answer. So you could say, hey, that thing is on its way to 0, and then subtract a negative. And so I could say then that Rn is less than that answer I just got, which is 2 over the square root of 5. That's kind of cool. In other words, there's an error for my S of 5. And by the way, I shouldn't say Rn because I chose n to be 5 here. And of course, if I bust out my machine just to satisfy myself at the answer to this, whoa, that's 0.894. Now, my error is less than that. How much less? I don't really know. But notice, to Raymond's point earlier, this one is not converging very quickly. Therefore, this is not a very accurate answer. So my error is less than that. But I don't know how much less.
So then to answer the original question, would we just be looking at how close the equation is to the baseline of 1 over x, and then for that to know how fast it converges and thus how many times we need, or how far into the series we need to go?
Well, let me show you something even better. What if we wanted to be accurate in the original question to 2 decimal places, which is really code for 1/100th, right? Isn't that what it means? Like that's our error. In other words, we wanted 0.894 to pop out as 0.01. Does that make sense? We want to be more accurate than that. Is there a way to do that? I bet you some of you could figure this out based on what we just did. Is there a way we could do that? In other words, we were sort of wishing, you know, kind of like, darn, this isn't 1/100th. Is there some way we could make that be 1/100th?
In your integral, instead of 5, would you put in a bigger number?
Bam. In the integral, couldn't we just put in a bigger number than 5? And even more cool, do we have to just guess and say, well, let's try 15, darn, let's try 27, darn? Could we just not put a number in there? And just try to make it be equal to 1/100th? Like, could we make an equation out of that and solve for n and not even have to guess?
Hey Doug, why couldn't we do 1/100th equals 2 over square root of 5, or 2 over square root of x? Excuse me.
That's exactly right. Like, we already took this integral. Does that make sense?
You already did the hard work.
That's exactly right. It's not like I don't have to start over here, right? I mean, I have to take that integral, but we did, and we got 2 over the square root of x, because infinity is still part of the problem, right? In other words, we still have infinity there. So it really comes down to then, this is just going to be 2 over the square root of n, and we want that to equal 1/100th, right? Well, just solve for n. So if I multiply both sides by 100 and multiply both sides by the square root of n, I get 200 equals the square root of n. Some of you would accidentally do something stupid here and square root both sides, but you should be squaring both sides, right? So I
Real
have
quick,
to square 200.
wasn't there 2 negative?
Yeah,
Or-
except for we were subtracting a negative.
Okay.
Good question. Thank you for saying that. So I'd square both sides, and the answer to this is very disappointing. This converges so slowly. Notice, remember, we said 1 over x to the first didn't converge at all. And 1.5 isn't that much bigger. Does that make sense? So bad news. You need 40,000 numbers to add together if you want the answer to be this accurate. But at least you have something to do, right? Now, in Excel, is that terrible? Not really. That's actually not that terrible. For those of you that have any computer skills, you could write a program in your graphing calculator that would add these, just a recursive formula that just, and notice the word recursive, that just adds 1 to the number down below and then raises it to the 3/2 power and then adds it to the previous answer and then increments the n value to the next number and then does it again. Like, you don't have to have Excel with 40,000 lines here to do this. Again, that's just if you've spent a little bit of time with computers. I'm relatively terrible and I can do that. I could do that one pretty easy. So that's sort of disappointing, but just for the fun of it, let's consider it sort of a second question. What if we pick something that converges faster? So faster would be something like, I keep saying 1, but it doesn't need to be 1. Let's make it 5 this time, or 6. Instead of 1 over x to some power, remember we aren't going to use x in this context. Let's use k this time. K equals 1 to infinity. But let's raise it to some higher power. You know, we already know the answer to 2, but let's go to 3 or 4 or something like that. Let's go to 3. So that's going to converge quite a bit faster. I wonder how much faster. And so we're sitting here saying, I would like my error to be 10 to the -2. I only say it that way because your book's going to say it that way, and that could look confusing. That's 1/100th again. That's 0.01. And we're going to go, we want to go find n, you know, or I guess in this case, k. We want to find k. What value, you know, do we need to add up? How many terms do we need to add for this to happen? Let's see, is that a good way to say that? I don't think it is, actually. Again, there's more than one. We had this happen the other day. Find n. In other words, what term do we need to add this to? We've already decided k is all the numbers from 1 to infinity, right? 1, 2, 3, 4, 5, 6. So I really can't reuse that letter. It's not very clear. So then we say, okay, great. We need to take the integral of this statement, 6 over, and again, you could use k if you wanted to, that's fine, but I'm going to use x. Take the integral of that from n to infinity, and we would like that to be equal to 0.01, 1/100th. 1/100th is probably a better way to write it, since when I'm solving it, I'll be multiplying both sides by 100, probably confuse me less. So let's see, can I do this? I'm just going to scratch work this really fast over here. So that'd be 6x to the -3. You add 1 to that, that'd be -2. Then you divide by -2, so that'd be -3 over x squared. Is that right? So it'd be -3 over x squared, evaluated from infinity to some number. We want that to be 1/100th. So as before, when I stick infinity in this, I get -3 over infinity squared minus -3 over n squared. And because, as we have seen before, this is on its way to nothing, then I really just have this statement. Since it's minus a minus, I really have the statement 3 over n squared is equal to 1/100. So if I multiply both sides by 100, I get 300 equals n squared. This time I get to square root both sides, and I'm going to get a pretty reasonable answer this time. The square root of 300 is only 17.32. Now, interesting question. I want to be sure I am accurate to the 100th place. This came out of decimal. Is the answer 17 or 18?
I'd go with 18 just to be safe.
Yeah, the right answer to this is actually 17.3. but you know, there's no such thing. You can't have S to the 17.3. There's only whole numbers. Does it make sense if you did something foolish like 15, then your error is going to be more than 0.01? In other words, if you go down, doesn't your error go up? If you have too few terms, your error is too big. You can't go down. So we can't go down to 17. I don't care. You don't round that off, you round it up. In other words, if you want to be sure you're accurate to the 0.01 place, even if that's 17.01, you're still going to call it 18. So this is always going to need to be rounded up. So we would say, sweet, we only need 18 terms of that sequence. And then we would actually have an answer that we could kind of verify, we can kind of prove, if you will, is accurate to the 100th place. Now, what I'd like to do to give you a second to think about this is, let's actually go do this. Let's go do this in Excel and add the first 18 terms and kind of see what happens. Again, this is just so much simpler than books make it seem. So I'm opening up an Excel. I am sharing my other screen. And since this is so reasonable, and again, like, does that shock you at all? It's like, what, the last problem, it took 40,000 terms to get the answer correct, and this one only took 18. That's because when you cube something, those numbers grow fast, right? 2 cubed is 8, 3 cubed is 27, 4 cubed is 81. So we're like 1/81. Like, those numbers are getting small really fast. The individual terms are on their way to 0 really fast. Therefore, it doesn't take near as many terms because each term begins to be worth not much really fast. So let's see here, as we have done in the past. I need 18 terms here. Let's feel it. Boom, that's 18. Not even close. What a surprise. I'll just leave them there. So our first term was equal to 6 divided by that number over there raised to the 3rd power. Boom, there's our first number. So when we put in 1, we get 6. When we put in 2, we get 3/4. I think this is a little important that you understand this. What's the title of this column right here? What are those in the language of this?
A.
Close, not A. This
Is that
one
our
is
n
A.
value?
This one is A. Eve's right. This one is our n. In other words, our n's are 1 and then 2 and then 3. And then the A is the equation that once we put in the 1, 2, and the 3 pops out our answer. Does that make sense? Again, I don't think that's obvious. I'm not surprised that.
Oh, that's what I thought you were referring to.
And then if I start adding them up, then these are actually my sums, right? So for instance, if I write a formula as I did the other day, equals sum of, and this particular one right here would be the sum of all of these combined. And to be able to copy it, if I go put some $signs in front of that. Oh, I had it, and then I had to go do something stupid. D3. I never remember to hit return. Boom. What's wrong with my formula? Struggling hard today. Let's see, that's supposed to be D6. This is supposed to be D3. This is supposed to be F4. There we go. So does it make sense? That's S4 for our number. And notice the fact that I put a 6 on top made this a really big sum because the first one was 6. So this number, this is n is 4. This is the 4th term, and this is the first 4 terms added together. Does this language up here make sense to you? Like if you see that in the book, are you thinking, you know, bam, I get that?
Yeah.
Cool. So now if I drag this down to 18 terms, what are you not surprised to see down there at 18? You're not seeing an error here. You're just seeing a small number. Does it make sense? There's no way that number could be like 0.2 because we're about to add another one of those. Like when I move to the 19th term, I'm about to add another number to that, right? And so that next number better be darn small if I'm saying the sum here is already accurate. Now let's drag this down. Boom. So what we are saying is that answer right there, 7.203582, we're saying that answer is accurate. It's not going to be off. It's not off from the real answer, which we will never know. That's a lie, by the way. Somebody has found the formula for 1 over x cubed. Even though we'll never know the answer, the actual answer to this question, we can at least say, hey, there's an answer that was reasonable. It only took me 18 terms to get it. And I know it's accurate to less than 0.01. It is not off by 0.01. Otherwise I'd add 0.01 to it and I'd have the perfect answer. It's less than 0.01. That's kind of cool. Can we see that this is true? Well, look at the next answer. See how they're the same to the 100th place? Now, are they the same to the 1000th place? No, because we said we didn't want to be accurate to the 1000th place. So of course it didn't change by more than 100th, right? Of course they're sitting there accurate to the 100th place. So it's working. You see what I'm saying? Now, what I'm a little curious about, and I'm a little hesitant to do this in case it somehow doesn't work, but let's drag it down. Let's drag it down a little further. So I'm going to drag it just to 100. Notice, what's your thoughts on that? So would you agree that answer is more correct than the 18 answer? So we quit at 18, and I'm going to type this in my calculator, 7.203582. And we quit at 18 terms. And some other nerd said, I'm going to quit at 100 terms. Is their answer better? Well, of course it is. They spent more time at it and got it accurate. So of course theirs is bigger. And notice it's growing its way up to the correct answer because you're adding more terms. But if I subtract those two terms, 7.212044, what do I get? I get 0.008. Notice it's, if you will, working. If I keep going forever, way longer than this, the difference between the correct answer, in other words here, the difference between S100 and S18 was 8/1000ths. Well, that's less than 100. So it's working. Do you see what I'm saying? And notice how small the terms have gotten. The individual terms are teeny out here, and therefore they're not adding much. You see how powerful this is? You see that's kind of cool? Like I'll never know the right answer, which is disappointing, but at least I can get an answer as accurate as I want to. What do you think?
Wait, so what's the actual formula for 1 over x cubed? I'm curious to where this is going.
Yeah, this particular one does have an answer. I was actually quickly Google searching right before class to find it so that I could kind of point that out to you, but I couldn't find it again. I might have written it down somewhere, but it's Google searchable if I get a second. Oh, wait. No, I don't have it written down anywhere. If one of you finds it while we are here, or I do, let's get that out on paper. So cool. So just to kind of record a little bit of what I just did. So that S of 18 was 7.203582. S of 100 was, and I say approximately because the decimals go further out. I'm just getting what the calculator, what Excel gave us. And when I subtracted those two, does it make sense? I should not get something like 0.03 because then that shows it's not accurate. So that can't be the case. But I actually got approximately 0.008. Yeah, that's, I need these two to be zeros. Does that make sense? Otherwise, that means this formula is not working. And then the other thing that I think was kind of salient about this is the actual 100th number was 1, 2, 3, was 1, 2, 3, 4, 5 zeros and then a 6. So yeah, when I'm out there, I'm not adding very much anymore. And that's because 100 cubed, 6 divided by 100 cubed, tiny number, right? So it's working. That's cool. So be able to find the error, be able to find for a given choice, and then be able to find n for a desired error. Okay. So this would be something I would not want you to memorize, but that's a formula that we would need to know. Okay. So the other thing I want to show you today is one more convergence test. And it is what we've been discussing. So I'm hoping, and I would invite you to discuss this with me. I'm hoping that you can look at this one and say, duh, if the individual terms don't go to 0, we just saw that A of 100 was really close to 0, then adding them up is foolish, right? To expect that it's going to converge. What's with this comment over here? This test is inconclusive if it is 0. Like, does it automatically mean it's going to converge? Well, remember the 1 over x one? Remember how that did not converge? Yet, don't the individual terms still go to 0? Like, isn't 1 over infinity on its way to 0? So just because that happens doesn't mean it automatically converges. So that's why it says it's inconclusive. Just because the terms go to 0 does not always mean it'll add up to something. Just because I'll probably forget to say it and I didn't say it yesterday. And actually, there's a good reason for this, and I just don't know what it is, but that series is called the harmonic series. And I think it has to do with musical notes. But anyway, I don't want to go into that. That series did not converge. And it was actually because of the integral, because we took the integral of 1 over x and it was infinity. And the area we were after could be considered to be larger than that. So there's no way the finite sums, the Riemann sums are going to add up to something. And so that's why it says it's inconclusive. Again, I want to show you the sheet because you're going to have the sheet on a test and I want it to speak to you. Geometric series, we said, yeah, those will add up to something. We have the ability to add them up. Not only that, they even told us what it converges to. As long as your x or your r value is less than 1, it will converge. If it's more than 1, it will diverge. But not only that, we can actually find the answer to it. Very satisfying. You actually have an answer. It converges to something. P-series test, we've just been playing with that. As long as that p value, n to the p, as long as that p value is bigger than 1, It's going to converge to something. That's really cool. And finally for today, the integral test. Let's just read it in this context. So they're saying you got your formula here and you're going from something to infinity. Notice it doesn't have to be 1. You could start from 5. You could go from 5 to infinity, 9 to infinity. Pick C to be anything you want. Doesn't make any difference. By the way, if you started at 5, does it just make sense you just left a few of the numbers off in the beginning? So that isn't really going to change anything. Those numbers are finite numbers anyway. The answer we just got a minute ago was like 6 point something, right? And that's because that first number was a 6. And so I went from 1 to infinity, but what if we went from 2 to infinity? Does it make sense the 6 would have just been missing and our answer would have been the same answer we got, but just 6 smaller? So it's like that extra number in the front doesn't really make any difference. It isn't going to cause it to not converge. It's just going to make the answer larger. So you can start any place you want. And what is this saying? It's saying it converges if the integral converges. This statement right here. In other words, the series itself will converge if the integral converges. And if the integral diverges, then the series converges. In other words, the series will converge if the integral converges. The series will diverge if the integral diverges. It's saying that exactly because of this same figure right here. This figure shows the point, and we've been playing with this. This is conceptually not new. So would you agree in this picture that this series is less than that integral? Again, these are really the same thing. Those are really the same equation. But because this is a right-hand Riemann sum in this picture, then if the area under the black curve, in other words, this over here, if this area is finite, finite just meaning it has an answer, not infinite. Finite's the opposite of infinite. If that's finite, and remember we said the integral of 1 over x was infinite. So that didn't work. Therefore, because of the integral test, we said, well, then our answer is not going to work either. But if it does work, if it is finite, then of course, since an is less than, then it's also going to be finite too. Now, again, all this really says is it will converge to something, but it doesn't answer the question, what does it converge to? We don't know. That's why this error thing is kind of cool. Now, let's think about this for a second. If this area here is smaller than the integral, if the integral diverges, isn't this smaller? So if it's smaller, then maybe it converges. Do you see what I'm saying? Does that bother you at all? I mean, remember 1 over x was just barely too big, right? Just barely, like it almost converged, but not quite. And we said yesterday that not 1 over x, but 1 over x to the 0.01, it barely converged. It barely actually added up to something. So if this area here is a little smaller than the integral, then is it possible that this would converge? And the answer to that has to do with, well, this picture up here. In other words, if you just take one term away, I don't know how complicated I want to make this. If I switch this so that, the integral is kind of, it's up here. If I move from n to n plus 1, and I sort of think of it as an upper integral, does it make sense? That's the same answer as before. It's just missing the first box. That's the same answer as the orange area. It's just missing the first box. And now all of a sudden it's above the curve. So the point is, it doesn't make any difference if you add one box to it or not. It isn't going to change the outcome of the infinite series. If we're adding them up and you add one more box that's worth 20 or whatever, that isn't going to change the fact that the ultimate answer goes to infinity or not. What's causing infinity to happen is, this business way out here. It's the stuff out to the right. Whether it settles against the x-axis quickly enough is what causes it to converge or diverge, not whether there's a box or two extra at the start of the problem. And so that's why we can ultimately say that if one converges, the other one will too. Again, I'm just trying to give you a simple kind of a conceptual understanding of this, not a proof. So these first 4 tests are what you need to understand. This one is 10.5, which we'll actually do tomorrow. And I am going to be, I'll send you an email about this, but I am going to be gone Monday. So as it turns out, I think we're doing okay, because I was going to talk about 10.4 again tomorrow, but since we got to start on it yesterday, I don't think we will need to. So we'll talk about 10.5 tomorrow, and then you'll have Monday off. So we'll talk about that one later. But these first 4 you need to understand. So let's just go play with the integral test a little bit more. All of that should sound pretty theoretical to you, but let's just look at an example, because I think the example will answer the question a little bit better. Let's say I was looking at this, k over e to the k. Well, k went from 1 to infinity. And from our discussion the other day, do you see this fraction? And a big part of these problems will be fractions. What do mathematicians call this kind of an equation? And maybe to help you with that, I'll even throw a number in front of it, like a 4. What do mathematicians call that kind of equation? 4x, in other words. Again, you're not used to seeing k, but what if it's 4x? If I said y equals 4x, what do you call that? Hey, that makes a what?
Linear.
Linear. What about the bottom one?
It's exponential, right?
Exponential. I like that you said right. You're willing to speak up and go for it, but you're not sure. I love it. Exponential. From that Excel I showed you the other day, which one of those grows faster?
Obviously linear.
Exponential outgrows linear. Let's take another quick look at that. Let's not take a look at that. So you might have the intuition, if you will, that the top is going to grow a lot slower than the bottom. Now, a minute ago, we looked at 1 over x squared. Well, notice the top's not growing at all. It just stays 1, 1, 1, 1. It doesn't grow at all. And the bottom was squared. And so, it was growing, but the bottom didn't grow at all. And so because the top or the bottom outgrows the top, would you agree that our a to the n, this is our a to the n, or in this case, a to the k, would you agree it's on its way to 0? And again, I should, I guess, technically say as k gets bigger. And again, you can easily see that. Notice in the beginning, that's not true. Like if you put 1 in, you get 4 times 1 on top, which is 4. And on the bottom, you get e to the 1, which is 2.7. Like in the beginning, this thing isn't 0. But as soon as you get out there to like 5, well, 4 times 5 is only 20, but e to the 5 is already a pretty decent sized number. And so it's definitely on its way to 0. So it passes the divergence test. The individual terms go to 0. So this has a shot at adding up to something. But again, we can't just say that it will add up to something. So then we say, okay, cool. Well, does it actually converge? It's not geometric. If you write out the first few terms, it's not a geometric series. It's nothing we've ever seen before. I just kind of made this up. Well, the integral test will tell us that. If we find the integral from 1 to infinity of that, and it actually comes to an answer, then we can say, then that will too. So the integral test says, if I take the integral, and again, it's kind of common. I'm hoping this is making sense to you. When I say k is only whole numbers, 1, 2, 3, 4, 5, 6. If we rewrite this with x's, which isn't ultimately necessary, and we say from 1 to infinity, do you understand that x is not just 1, 2, 3, 4, 5, it's 1 and 1.1 and 1.2, it's everything, right? That makes a smooth continuous curve. This is not Riemann sum anymore. This is literally the perfect area under the curve. So then I think, uh-oh, can I even take that integral? Like, and so part of this class is going to be, can I still take integrals? Wow, that feels terrifying. Like, how do I take the integral of that? Remember, we do not like multiplication and division, because remember in derivative world, that was like quotient and product rule. So I'm finding myself going, oh no, can I take the integral of this? I would be, this is an utter guess, but I'd be willing to bet every one of you is like, I'm not sure. Anybody have any good ideas? What are we gonna have to do to take the integral of this? This is terrible.
I'm thinking we're gonna have to do some parts.
Bam.
Yeah, I'd go for partial integration.
If I rewrite this like this, so it looks like a multiplication, then I think this is integration by parts. Remember, integration by parts' strength is, in my way of teaching this, if you let this be the u and this be the v prime. Let me see what was, I'm going to make this for myself because I think this is the kind of thing you should be able to do. I don't remember integration by parts. Actually, I'm pretty sure I do. But
uv minus the integral of v du.
yeah, watch me make this really quick just in case you need to make it for yourself. Isn't this what the product rule says? If you have the integral of two things, I'm sorry, the derivative of two things multiplied, this is the product rule, then it's the derivative of one times the second one left alone. Well, all I need to do is resolve this. Well, take the integral of both sides. If I take the integral of both sides, the fundamental theorem of calculus says derivatives and integrals are inverses. So if I take the integral of the left side, then that derivative's gone. If I take the integral of the right, then I have the integral of both of these terms. And if I solve this for this one, that's integration by parts. There, I just made it for myself. Vale either had it written down or had it memorized and correctly just said it. But I made it for myself. That's really powerful. Can you do that? It takes 2 seconds. Notice I had to have the product rule memorized to pull that off. So then what I'm saying is, cool, if u is for x, then u prime would just be 4. If v prime is e to the negative x, the integral of e to the x is e to the x. Except for I also have to divide by the derivative of that, so I think it's negative then. Is that right? Let's see, is the derivative of negative e to the negative x? Yeah, that's right, because it'd be e to the negative x, but then times -1. Yeah, that's right. So I have everything I need now to go kind of, basically I'm saying this problem, my friends, is too hard for me. Notice I'm being lazy, not putting dx on there. So instead, I just wrote that. Instead, I have u times v. Well, there's u and there's v. So there's u times v, which I don't care how ugly that is because I don't have to take its integral. The question is, will this new integral be easier? Well, u prime is only 4. That's the strength of this. So I have 4e to the negative x. Yeah. Easier. I can do this one. Notice the product rule essence of this is gone. So I can say awesome. And the integral of e to the negative x is negative e to the negative x. And so I can say then, if I copy this beautiful integral down here, I can say then that is equal to negative 4x e to the negative x plus 4e to the negative x. Found it. And now I can evaluate that at infinity and at 1 to see if it has an answer. Now, to write that in a way that might help me think about this a little bit better, isn't it true that this would be negative 4x over e to the positive x? And I could even factor the e to the x out if I wanted to. Yeah, actually, I think I do. This looks even nicer. 4 minus 4x over e to the x. Isn't that even nicer? So again, what we're trying to decide is, does this have an answer? So if I plug in infinity and I plug in 1, of course, the important thing is what happens to this first term here? Well, look on the top. 4 times infinity. That's a big number. That's an infinitely large number. What about on the bottom? E to the infinity. Would you agree that this 4 right here kind of doesn't matter? Well, this is where what I said before is so important. The top grows way more slowly than the bottom. You got to have some intuition to this. And again, we can't put infinity in, but if you said 1,000, 4 times 1,000 is 4,000. What's e to the 1,000? I'm typing that in my calculator right now. E raised to the 1,000. Notice 1,000 is not a very big number. My calculator says error. It's so big that you can't even tell you. So the top is only 4,000. The bottom is so large the calculator can't even answer the question. And I only stuck 1,000 in there. Exponential equations outgrow linear equations. So this whole term is on its way to 0. You agree with that? Are you okay with that?
Yeah.
And so this actually does have an answer. Let's see, it's negative everything. So I guess that'd be 4. Well, it's 4 minus 4. That's 0 on the top. That's kind of weird. I'm looking at this thinking, really, that's 0? Negative 0? I'm not going to take the time to graph it, but maybe it's something that looks like this, like it has some positive and negative area, like there's positive area and negative area. I'm not really sure. That kind of bothers me that it isn't a number. But it's kind of good because it doesn't matter that that's 0. The answer is it's not infinity. The key is whatever this number is over here, this number is not equal to infinity. So the area under that curve really does add up to something. So the integral converges. So based on the integral test, we can say the integral converges to 0, or I should just say it converges. So the series does to spell 2 right, 2 O's and 2. Now again, what's the answer to it? I don't know. That's the disappointing part of this class. What does it converge to? I have no idea. Could we get a bunch of terms and, you know, figure out the error? Yeah. Maybe we'll do that in a second. Just quickly, because I'm a curious human, I'm a little bothered by the fact that that answer was 0. I sort of feel like I did something wrong, but I just want to look at the graph really quick. I'm going to do it in the graphing calculator. You do this with me. 4 to the x from 1 to infinity. I just want to know what that graph looks like. It's like crazy clear. 4x divided by e raised to the x. Zoom
You
set.
got the you typed it in wrong.
I typed it in wrong. Thank you. I'll fix that. Yeah, clearly I did, because that answer is not approaching something. It's taking forever to graph it because it's such a crazy number. 4x, 4x. Yeah, I said raised to the power of, not divided by. Come on, man, concentrate. Again, this would be so much better in Desmos. So notice the graph is laying down against the x-axis very quickly, so I'm not surprised. However, the area under that thing from 1 to infinity is not 0. Do you agree with that? Our answer for 0 is wrong. But it does converge to something. So what was bothering me was probably good to bother me. That means I made a mistake in the integral someplace. That's probably worth us fixing. Let's go fix it. Did anybody see it? Did anybody see me doing something wrong and just didn't say anything about it?
I didn't notice it anywhere. That was weird.
4 minus 4x. Actually, let's cheat in the calculator here, since I still have the calculator on. If I say, let's see, where was that? Second calculate. What is the area under this curve? In my case, I can only say from 1 to 10 because that's as far as my screen went out. So lower limit 1, upper limit 10. I could reset my screen, but that's saying 2.94. So we should not have got 0.
Did we move the negative out front of the e when we took the integral of e to the negative x?
Yeah, let's troubleshoot that. Did we get the negative sign right?
Oh, we didn't. I see what he's talking about.
What's wrong?
I think we're supposed to, just after the parts, when we were plugging the terms in we got for parts, we forgot in our
Well,
integral a negative.
The integral of this e to the negative x is negative e to the negative x, and that negative cancels with this negative, making that a positive. Is that what you're referring to?
Oh, yeah, never mind.
Right, so v was negative e to the negative x, right?
Yeah. Yeah, v is negative e to the negative x.
Which makes that a plus the integral of 4e to the negative x, right?
U times v. Ah, yeah. Okay, it is a negative. So I think you said this from the beginning. But v was negative e to the negative x. Integration by parts, that was already a negative, right? So this was supposed to be a negative. Therefore, those negatives cancel. So this becomes a positive. So that's actually a positive. Then we take its integral and it actually turns into a negative. Again, don't you make mistakes like this? Like, that's why technology is so cool. Like I got lucky that I got 0 because I thought, what? The area under the curve is 0? That doesn't make any sense. If I'd have got something like 2, I wouldn't have known I made that mistake. So
Yep,
let's see.
all the time.
Yeah. So that becomes, that changes this sign to a negative, which makes them both negative. Aha, now we're getting somewhere. So that still goes to 0. This becomes minus a -4, and then it becomes, I think, 8.
Yeah,
So it's 8 over e, right?
that looks a lot better.
Now that, and again, we don't really care in our class, we don't care what the answer to that is. We just care that it's not infinity, right? But on my calculator, 8 divided by e is indeed 2.943. And so, okay, that agrees with what the calculator said. And so good, I didn't screw that up now. So the point is, it's not infinity. That's all we really care about. And so therefore, that means because the Riemann sum is below that, it's under it. It's under that curve. Then that means our answer must converge to, let me show you one more cool thing. Kind of a visual on this that I think I still have up. Bam, there it is. So this is a Desmos visual of a Riemann sum. Notice this is the equation for 1 over x squared, but let's change it to what we were just working on, 4x over e raised to the x. So that black graph is the same graph we just saw on a graphing calculator a second ago, but of course way uglier in the calculator. And the green is the Riemann sum. That's us adding them up. Do you agree with that? We put in 1, we put in 2, we put in 3, we start adding them all together. Well, it's under the black curve, right? So if the black curve converges, then so is the Riemann sum. That's what integral test says. Really simple. Now, would you agree that this black curve is approaching the x-axis ridiculously quickly? Do you agree with that? Ridiculously fast. So you can just tell by looking at it, it's going to converge. The black graph is going to converge. And notice you can see the boxes out here, but look how tall they are. They're really short. They're so short that you can't even see them. By the time you're only out at 12, we're out there at x is 12 and you already can't see them. As a comparison, if I go down here and I graph the equation y equals 1 over x, notice how much more slowly, remember that was the line, that's the line between things that don't converge. That goes to 0 so slowly, even though it is going to 0, it goes to 0 so slowly that it actually still has an infinite area, Gabriel's horn. And notice the black curve is way steeper than that. So just by comparison, just by looking at it, the black curve is certainly going to converge. And so that's why the integral test is so cool, because the sum of the finite series is less than the integral. So the integral test is kind of cool. What do you think? A couple other just quick ones. I see we're out of time, but I can show you a couple of things really fast. You have 4 tests now to see whether something converges. So examples like this one. All we have to answer is not what is the answer, but does it converge or not? You should be able to tell me that based on the tests that we have to choose from. What kind of a series is that? Or what kind of a test applies in this case? Now, I want you to think about this. The tests are kind of ordered in the sense that you first want to make sure the terms actually go to zero. Check that first. Do those terms go to zero? Secondly, is it geometric? And then P series is way easier than integrals, right? Like you got to take an integral. Like that was a pain. I got it wrong, right? I'm the teacher. So I don't want to proceed down the list here and kind of do the easiest ones first. And so would you say that that goes to zero? If n is 6 and then 8 and then 50, are the individual terms going to zero? The divergence test? Yeah. The cube root of infinity is infinity. The terms are on their way to zero, so I can't just punt right there. Won't take the time to look at it, but it's not geometric. What about the P series test? Does it work? Well, yeah, this is a P series. What's another way to write that? 1 over n to what power?
3 halves?
Not halves.
Or is
The
it-
cube is cube rooted. It's 1/3. So if this wasn't there, you would have said to the 1/2 power. Because the 3 is there, it's to the 1/3 power. Well, there's your P. Is that P less than 1? No. It's got to be bigger than 1, right? So this diverges. This diverges by the P test since P is less than 1. Done. So don't bother trying to add them up because it goes to infinity. That's kind of the idea in the section. I got some other examples I'd like to do, but maybe we'll pop those in really quick first thing. What would be wise for you, I think, is to go, can you go do the 10.4 assignment? Again, you don't owe it to me till Sunday night, but this is a very bad time to wait till Sunday night. Like play around with this some. I'd love to start tomorrow with you saying to me, hey, I couldn't get number 7 or, something of that nature. But you really need to practice this stuff now. We've looked at it once, but can you play around with it and see it work? That's what I'm after.
We've learned everything to finish the 10.4 homework, right?
Yes, you should theoretically be able to do everything. You should be able to do 10.4 now by yourself. No problem. Okay. 9:25. Get out of here. We'll talk more.
Thanks, Doug.
Have a good day.
Thank you.
See you tomorrow.
See you tomorrow.